Welcome to my YouTube channel. My name is Ujara Joseph, a teacher of physics. Today still, we are going to look at ladders, and this time round we are going to look at the second number on ladders, and it's right here. It tells us that one end of a beam of length 4 meters and weight 100 newtons is hinged in a vertical wall. An inelastic rope is tied to the other end of the beam and is fixed at a point 4 meters vertically above the hinge. The weight of 300 newtons is suspended from the beam at a distance of 3 meters from the hinge. Calculate Roman 1, the tension in the rope, Roman 2, the reaction of the wall on the beam if the beam is kept horizontal. And they are telling us to assume that the beam is uniform. So what we are going to do, we are first going to draw the force diagram showing the necessary forces acting on both the beam and the rope. So we'll first, so they're telling us that there is a vertical wall. If I draw this as my vertical wall, and then they're telling us that our beam is hinged on a wall. So we shall have a beam at this point. So this is our beam. Let me call this end of the beam A and this other end of the beam B. So and they're telling us that the beam the rope is being tied at the other end of the beam, and it will be at a point which is 4 meters above the hinge. So if I draw the inelastic rope here, so it means since this is a rope and is inelastic, so our tensional force acts along that. So I'll call this is point C, and if this is my point C, the distance from here up to this other side is 4 meters. They're telling us that we have to assume that the beam is uniform. So it means that our center of gravity is in the middle, and that is where the weight of the beam will act. So if they're telling us that the weight of the beam is 400 newtons, 100 newtons, and then it is of length 4 meters. So it means this weight will be at a point which is 2 meters from the either ends of the beam. So I will have, if this is the midpoint, this is my G, and this is where the 100 newtons will act. And then they're telling us that the weight of 300 newtons is suspended from a beam at a distance of 3 meters from the hinge. So if this is the center, so this means that this will be 2 meters up to here, and 300 newtons is hung from a point which is 3 meters from the hinge. This is our hinge, and so we shall have 300 newtons at that point. So we shall have, this will be, to make this 3, we shall have, this is 1 meter, and this is another 1 meter to make 4 now. Good. So I'm going to make this, the angle that the rope makes with the beam, to be theta, and then the angle that, of course, at this point, there is the reaction that is being offered by the wall on the beam. And so there will be a reaction at this point. I'll call it R, and it will be acting like that. So you realize that at this point, the tension on the rod has two components. It has the vertical component, and then there is the horizontal component. And if I'm to put it, I'll have this will be in terms of this angle. This is, since this is our hypotenuse and it makes a right angle at this point, this will be T sine of theta. And this other component, which is the horizontal component, will be along this, and this will be our T cos of theta. The same applies to our reaction. It also has two components, the vertical and then the horizontal. And if this is angle alpha, so we shall have, this will be R. Since our hypotenuse is R, we shall have this will be R. It will be R sine of alpha. And then this other horizontal component will be still R cos of alpha. So I think we have included all the forces that are acting on both the rod and then the beam. So, and since the beam in equilibrium, then the resultant is 0. So we are going to consider, first of all, the translational equilibrium, and then later we consider the rotational equilibrium. Now, considering we shall have, first of all, resolve vertically, and then we come horizontally. So resolving vertically, we shall have that there are forces which are acting vertically upwards. There is a T sine theta and then R sine alpha. And then those ones acting vertically downwards, we have 300 newtons and then 100 newtons. So therefore, I will have that T sine theta plus R sine alpha equal to 300 plus 100. So in this case, you will see that this will be T sine theta plus R sine alpha will be equal to 400. And I'll call this is equation 1. Then we are also going to consider resolving horizontal. So horizontally, we have this. If you consider this R cos theta, cos alpha I mean, is acting towards the left-hand direction. And then T cosine cos of theta is acting towards the left. So those forces are opposite to each other. So it means T cos of theta is equal to R sine of R cos of alpha. So we are going to call this equation 2. And then, if you consider a triangle which is ABC, you will see that I will have something which looks like this. That is a right angle at this point. This is point B. This is my point C, and this is my point A. You'll see that this is where the tension is acting. This is 4 meters, and this is 4 meters. This is where our theta is. So if I want to find theta, I'll have to get a tan of this. So if I'm to get a tan of theta, this is the same as opposite over adjacent. So I'll have this is 4 out of 4, and this implies that I'll have this is equal to 1. So my theta alone is a tan inverse of 1. And if you press from your calculator the tan inverse of 1, this is going to give you 45 degrees. So meaning our theta alone is 45. So now I'm going to take moment about one of the points, either point A or point B. I'm going to take moment about point B, and then we see if we can easily get the tension. So considering now the rotational equilibrium, I'm going to taking moment about point B, or taking moments about point B. So you realize that this is our point B, and this is where we are taking the moment. So I'm going to start with the furthest, this one, the tension. If I'm going to take tension, then I need its perpendicular distance from the turning point, which is B. And you cannot tell me that the perpendicular distance of T from the turning point B is 4. No. So it means we are supposed to draw a line which meets the line of action of tension from the turning point. So if I'm to extend, I'll have this. Let me call this point my point S. And it makes a right angle at that point. So the perpendicular distance of the tension from the turning point will be SB. So it means I'll have, and if you check on tension, it will take the beam as if it is the only force acting on the beam. You will see that it will take the beam in the clockwise direction. So clockwise is negative. So I'll have negative T times the perpendicular distance from the turning point, which is SB. And then plus, the next force is the one of 300 newtons. Now, 300 newtons, its perpendicular distance is actually 1 plus 2, which is 3. And if it is the only force acting on the beam without this, so you will see that it is going to take the beam in the anti-clockwise direction, which is positive. So we shall have 300 times 3 plus. Again, the next force will be 100. Even when you look at again 100 newtons, it will still take the body in the anti-clockwise direction, so which is still positive. So I'll have 100 times the perpendicular distance, and the perpendicular distance is 2. And then finally, of course, we shall have R. but if the perpendicular distance of R from the turning point is 0, so that will give us still 0. So it means this, I'll equate this to 0. So SB, I'm going to take it if I'm to consider this. So this, it means SB is opposite to this angle. So it implies that and our hypotenuse is 4. So SB, we are going to use a sign. So SB is 4 sine of theta. So we shall have that negative t times 4 sine of theta plus, this is going to be 900 plus 200, which is equal to 0. So you'll see that this is negative 40 sine of theta is equal to 1100. And if this is having a negative, when you take it the other side, it becomes a negative. So it means my tension T is going to be 100. I divide by 4 times the sine of theta, but the theta we already got it at is 45. So if we are to press from our calculator, you will see that 100, and then we are dividing by a 4 sine of 45. This is going to give us the tension which is equal to 388.9 newtons. So we have managed to get Roman 1, which is the tension in the rod. So the next is to find the reaction of the wall on the beam. So we already got, there are two formulas that we already got. There is this one, I mean the equation. There is equation 1 and equation 2. So if you say from, this is Roman 2, from equation 1, you will see that I have already T, which is, this will be 388.9, and then sine of theta. I have my theta, which is 45. So to be sine of 45 is going to be, I'm going to add R sine alpha, which is equal to 400. So you will see that I will have 388.9 and then sine 45. This is giving me 274.99. If I put to 3 decimal places, that will be 4 plus R sine alpha, which is equal to 400. So if I take this one the other side, I will have 400 minus 274.994. And then it means this will be R sine alpha will be equal to 125. I can call this is equation number 3. Then, if I'm to come to equation 2 again, from equation 2, I'll have that T, we have T, which is 388.9 cosine of theta. Our theta is 45, is going to be R cos of alpha. So it implies that if I'm to press this again, 388.9 cos of 45, you will still get the same thing, because a cosine of 45 and a sine of 45 will always give you the same thing, which is 1 out of a root of 2. So this is going to be 274.994 should be equal to R cos of alpha. And this is my equation 4 now. Now, I'm going to rearrange this. Let me not call it 4 from here. I'm first going to rearrange it such that it appears like this. So this is going to be R cos of alpha is equal to 274.994. This is 4. So now, I'm going to divide equation 3 by equation 4. So dividing we shall have so when you divide that, we shall have R sin alpha out of R cos alpha is equal to 125, and then I divide by 274.994. So this, when a R and a R will cancel, and then a sine of alpha divided by cosine of alpha will give you a tan of alpha. This when you divide 125 divided by 274.994, we shall have 0.45 for let me say 6. So if you're to get the tan inverse, alpha alone is the tan inverse of 0.4546. So for 546 is giving me my alpha is giving me as 24.4 degrees. So since I've got the value of alpha, I can use any of these equations that I've already got. Either this, or I can even use this to get the value of R. So I can say from equation 3, R sine of alpha, which is 24.4, is equal to 125. So it means if I'm to get R alone is the same as 125 divided by sine of 24.4. Then my R is equal to 125 I get it as 302.58. So I can round to 1 as 6 newtons. So that is our reaction being offered by the wall on a beam. You can as well would have taken a moment about point A and see and then follow the rest of the procedures the same way. Thank you very much. Subscribe to my YouTube channel for more updates.